Okay, let's get started.
Okay, welcome everyone to the first session for Vision, Introduction to CNNs. Uh, Today's learning objectives will be thus. We'll first discuss some applications of computer vision. We'll also discuss the motivation from digital image processing filters, which inspires convolution neural networks. We will then go on to see how we can implement convolution, the mathematics and the logic behind it. And then we'll go on to design like basic blocks of convolution neural network. We'll also discuss why convolutions are suitable for computer vision applications. Then we'll move on to a case study of image classification using CNNs. We'll then discuss a few of the advanced CNN architectures which have come in the past years and the progression of the architectures, how it has moved. And we'll also discuss some practical training techniques for training computer vision uh, problems. All right. So computer vision problems are of wide variety. They are like classification, localization, detection, etc. The classification is the very basic problem where, in the image, if we say this problem that is there a car or there is no car, and then there is like localization where like we are not only interested if there is a car, we are also find out where within the image the car exists. And of course that problem could be more complex, where there could be more than one possible instances of that object, or there could be even more than one instance of different types of objects. So there is a multi-class detection. Then also another variety of the object detection problem is like object segmentation, where we are just not only we are interested in the bounding box, like a rectangular bounding box, we are actually interested in which particular pixel. So the classification happens not at the image level or region level, but at pixel level, which pixel belongs to which category. So over the course different lectures, I think different topics will be uh, discussed to solve each of these problems. Then there is another category of problem where there is video processing, where images change with time. uh, we have to not only detect objects within a frame, we also have to correctly map the objects as they move, as they change positions from frame to frame. All right. So till now we have used like deep learning in previous lectures, during neural networks, but there are some challenges when we try to apply uh, like like dense networks, deep learning for computer vision problems. The biggest challenge that we get is the size of the data. So the dimensionality for image processing applications is huge. Let's say, for example, on the left is this image of a dog, and we want to build a classifier whether this image contains a dog or not a dog. And let's say very common, say size of image, say 1024 by 1024, which is actually small considering today's cameras, give like 12 megapixel, 15 megapixel images. This is just a 1 megapixel image. And for that we have the input layer dimension is like 3 million, and it is pretty reasonable to say that at least a 1,000 feature levels would be required, because as you can see, a visual representation is very complex. A lot of things can be happening within the image. And so even with a reasonable expectation of just 1,000 features, if you try to design a neural network, the input layer dimension would be huge. Like it would be almost 3 billion elements. And if we like 32-bit float used to store each of the weights, input weights of a neuron, then we'll end up with just 12 GB of memory just for the first layer of the network. So these kind of problems are very difficult to implement in dense neural network, especially with larger dimension and resolution. So that is one of the motivations behind using convolution. Of course, there are other advantages of using convolution for imaging. We'll discuss that further in our lecture today. So the motivation from using convolution, it's inspired from like
Yes.
very old signal processing techniques, which applies to digital image processing, which are called filters. So let's start with what is actually the convolution operation. So you can see that on the left, images within a computer are represented as a two-dimensional array of numbers. Usually the numbers are represented, like each pixel is represented with unsigned int 8. So the numbers could vary between 0 to 255. And what we call as a convolution operation in image processing context is applying a kernel filter on top of an input image. And on the middle, you can see that there is a matrix with some weights. So what it does is we put the kernel filter at different positions within the image, and using the kernel weights and the underlying image values, we do a weighted summation of that region which is covered by the kernel matrix and generate the output. And we move over the kernel matrix over different possible positions within the image and generate different output. So we'll discuss some of the very common imaging filters which has been used before the advent of convolution neural networks and deep learning for simple image processing tasks like edge detection. There are two variants of it, one for detecting vertical lines in the image, as you can see on the right, and one for detecting horizontal lines in the image. And so different filters uh, cause different mathematical operation. This is called an edge detection, also a gradient operator. And the output is different. Output is something which can be interpreted, which could mean different things. Another type of filter commonly used is like noise removal. For noise removal, that's a Gaussian low pass filter. And the weight matrix for the Gaussian matrix, one example of a 3 by 3 Gaussian matrix is thus. And as you can see, when you apply it on the left hand side image, it clears the uh, white noise and gives a much more smoother or cleaner image. There are other filters like sharp feature detection, which is basically a Laplacian operator on every location within the image. This enhances the regions within the image which are sharp. That means which has a lot of variations going on and non-uniform areas. And so the idea of filter, is different values of this kernel matrix can generate different kinds of output, and these are helpful in analyzing an image or deriving further uh, intuition into what the content of the image is. The concept of the filters gets extended, not just with one filter, but you can actually apply filters in sequence. So there's like we have seen the Gaussian filter, which is on the left, and on the right this is the Laplacian filter. If we process this input image via two stages, like first we apply the Laplacian filter and then we apply the Gaussian filter, we end up with edges within the image. So this is the contrast of the output is not so good, but I think if you look, you can see the edges of the image has been highlighted. So two-stage filter is able to give a different kind of like intuition into the content of the image. And extending that further logic, uh, very similar, not exactly a set of sequential linear filters, but very similar is a Harris corner detection. So it's even more complex operation. So edge is like very simple to detect. But Harris corner is a much more complex, filter, which came out in the 80s to detect corner points of objects. So in this object on the left hand side, there are geometric shapes, and we are interested to highlight the points where the corners means where two edges meet within the image. And this is basically a six-stage filter. Like you start with Sobel, and then you do gradient magnitude operation, then you apply Gaussian filter, then there is a function which is defined called Harris operator, and then there is a local minima operator. So once your input goes through, six stages of processing, the output is on the right hand side. So via a complex series of operators, we are able to detect or have much more intuition into the data, detect much more complex structures. So this is the motivation. Yeah,
Sumandeep, some people have a doubt
yeah.
that uh, that how do we decide which filter to apply?
Yes, yes, yes.
So I
I
think,
am coming to
yeah,
that.
we have to clarify that
I
these
will
are,
open the chat
yeah,
window.
that these are just examples, but actually we don't decide which filter to apply. It
Yes,
is automatically learned as weights of a neural network. So here
yes.
we are showing pre-neural network, before neural network, when all image processing was done using filters that were based on the expertise of the image processing engineer. Then that image processing engineer would choose a Sobel edge detector or a hard detector or some of these detectors. But we don't do that. So okay, I guess Sumandeep is getting to it anyway.
Yeah, yeah. So before the advent of application of machine learning in computer vision, most of the algorithms were designed by engineers based on their knowledge of the problem, based on their knowledge of mathematics. So then, in during that era, the filters were handpicked. That means engineers, based on their knowledge, would decide, what features are to be computed, and for those features, what should be the best filter weights. But in the modern era, when we are using convolution neural networks, what we do is we follow a data-driven approach, and we let the data decide what should be the filter coefficients. So it automatically learns the best filters, which would lead to the result we are seeking. So we use data to train to learn the filter coefficients at each stage. So, right. So as we saw, right, starting from single layer to two layer to like very basic algorithm like Harris operator still requires like six layers of filtering uh, to get to the results. So similarly, when we design, CNN architecture, where different there are layers of convolutional filters which have been determined using machine learning. uh, what it happens is the early layers tend to detect more basic and simple constructs within the image. Yes. The early layers detects like edges, corners, blobs, etc. And slowly, these set of base shapes build smaller parts of the object. So the mid layers detect, parts of the objects, and the later layers would build up like sub objects or the full objects made up of parts of objects. So this is what happens when you try to visualize like what the CNN layers do. And we'll now see how the convolutional operation is actually implemented and how we can reach at this stage. Okay, so some basic concepts of implementing convolution before we go on to building a convolution neural network. There's a concept called a valid convolution. So when you apply a kernel filter, so in this case, the image is n by n, or in this example, it is like 5 by 5. So let's say the input image is 5 by 5, and the filter is a 3 by 3 filter. And we are applying this filter on all possible locations within this image. And we find that there are only 9 unique positions where we can apply this filter. So the output from input is a 5 by 5 image, the output is a 3 by 3 image. And in the generic terms, we can define that if the input is n by n and the filter is f, then the possible locations where we can apply filter and compute the weighted summation is n minus f plus 1 cross n minus f plus 1. And this is called valid convolution because we are only taking the all the valid positions within the scope of the image where to place the kernel. As you can see that if we apply this, then the output is smaller. And then if we have multi-stage filter, what would happen is gradually the size of the image will decrease over multiple layers. And sometimes that is very undesirable, and or like it will rapidly become very small. So what we do is we have a technique in image processing, which is called padding. So to maintain the size of the input image same as the output, like maintain the size of the output image same as the input image, we pad the input image. That means we artificially increase the size of the image by adding additional uh, pixels along the boundary of the image, so that the number of potential locations to place the kernel filter on the input image matches the original input dimensions. So in this case, we start with a 7 by 7 filter. As we have seen that by a 3 by 3 filter, we tend to lose 2 pixels. So we have added a 1 pixel boundary all around the input image, thereby increasing the size by 2 by 2. And therefore now we have 5 by 5, that means 25 different possible positions for this filter. And the output image is same as the original input image, which was 5 by 5. And so whenever we pad, p is like how much we pad around the image. So p is like 1 pixel here. So the input image increases by 2p into 2p. And if you want to maintain the size, then p must be is equal to f minus 1 by 2. That means if we choose a filter of 3, so p must be 3 minus 1, that is 2 by 2. That means p is equal to 1, and so on. We can choose filters of size, say 5 by 5, and use padding of 2 pixels, and so on. Now,
Let's pause and take questions.
yes,
Gorang?
Stride. Is it the question?
Hello.
Hello, we are having a hard time hearing you. Go ahead. Okay, try again.
Am I audible now?
Yes. Yes.
Hello.
Yes.
So my question is like when we are doing padding,
Right.
when we are doing padding, even though our dimensions are not decreasing with
Right.
multiple layer,
Right.
but I think error will be accumulated along the edges.
Yes, it will be. So yes, it will be, because we are padding it and we really don't know what the actual value is. There are multiple techniques to padding, like it could be zero padding, like we just replace zero. Or there are techniques like we could extrapolate or mirror the pixel values along the border into the padded area. So it kind of mitigates the result, like the error in the possible error. But in practice, it is seen that that is still fine. Only the border pixels get affected, but like still it is all right. It does not have much of an effect.
But if we use like maybe very high deep like lot of layers,
Right.
like maybe 20, then also it will be fine.
It will have effect on it, and the effect will get propagated to the even the inner pixels if you as you move into the depth of the layer. But the like the amount, the percentage effect of that is usually not significant.
Okay, understood.
Yeah.
Thank you.
And of course, if you are, but generally zero padding is good enough. But if you are in a situation where like more computationally expensive steps you can do, like extrapolate the pixels around the border, take the values and extrapolate what the image could have looked like if the image was bigger, and that could be mathematically more closer, but it will also come at an expense of computation cost. So zero padding is the
So
most common. Mirroring is done, uh, and extrapolation is done. So these are common techniques.
mean value can be used, right? Average, like we can take a segment and put the mean of it in that
Could
place,
work. I mean, mean is
like
also a
running
kind
a
of an
kernel.
extrapolation, right? You compute
Yeah.
whatever formula. The extrapolation could be linear, bicubic. You can take a mean and then just replace those values. Or you can take a midpoint of the range, like 120.
Okay.
That should work. So any assumption pretty much works. Yeah. Strides.
Yeah,
Yeah,
sorry.
sure.
Ram Mohan, question.
Yeah.
Yes, sir. So my question was in this example in which it is shown two-stage edge detection, a Laplacian of Gaussian. So I
Yeah.
wanted to know if we can simply add two kernels and then directly like perform like directly hover the kernel over the image, the finalized kernel.
No, the kernel operation is not that way. So you like it's not adding the kernel, like it's like one pass and then two pass.
It's like
Theoretically, you could come up with a filter which could have, so the convolution operation, right, which we say in the terms of image processing context, is really a cross correlation operation, right? So the actual concept of convolution comes from signal processing, which is like, convolution in frequency domain is equal to cross like arithmetic
I got
summation in
it. I got
time
it.
domain and those kind of thing. So technically, the convolution that we use in image processing is cross correlation. So it does not have that like associative property. Associative and distributed the distributive property is not valid on that. So I cannot just add these two kernels and apply. If we derive the mathematics behind it, converting the problem into a frequency domain and then doing it and coming back, we could come up with a kernel, possibly a kernel value, which could have the similar effect,
Got it. Thank you.
right? But it will not be the addition of these two kernels. It will be a completely different value of the kernel. In some cases, it may be possible, but I don't think for the cost correlation thing, the associative and distributive properties hold. Uh, it holds mathematically, but that the actual convolution is in like signal processing domain, and in it's in like complex space and all that. Okay, so
There are more questions. Sorry, I
more
think people.
questions.
Tanvi, you had a question.
So actually, I didn't had a question. My internet went off from the time after what does convolution network layers do. Since I wanted that
I'm
part.
not able to hear. What is your question?
Hello.
Yeah.
So actually, my internet went off. So I wanted after the part of CNN layers do after that part. So if you
Okay.
could repeat that.
So basically, is everyone clear on convolution operation? So anyone who has a signal processing background actually might be a little more confused, because in signal processing we invert, we take the mirror image of the kernel as opposed to the kernel right away. But
Right.
here we don't complicate things, because anyway the weights are going to be learned. So
Right.
we just take the kernel as it is. So kernel is a two-dimensional array. It has a shape in the sense that it has some sequence of numbers within that two-dimensional array. So let's say 3 by 3 size, and it will give you we are just taking its cross correlation with a specific 3 by 3 location on the image array. That's it. That's all we are doing, right? So you can think of it this way: if your kernel if you divide by the if you make your kernel unit norm, it will have the maximum response if the image also has the same sequence of numbers as the kernel. So
Right.
if the kernel has negative numbers on the left hand side and positive numbers on the right hand side, it is seeking for that particular matched shape in the image. Okay, so it is looking for its own mirror. It's looking for its own copies in different locations of the image. That's what it is doing. If it doesn't find a copy, if it finds an inverse copy, like the negatives and positives are exchanged, then it will give you a low negative. It will give you a negative response. If it finds no shape correlation at all, then it will give you a zero response. If it finds high shape correlation, it will give you a high positive response. Is that clear? So some of these kernels could be detecting horizontal edges, some could be detecting vertical edges. There are vertical positive edges, there are vertical negative edges. Positive edge would mean that you are going from black to white, and negative edge would mean that you are going from white to black.
Right. So here, so I have not explained this thing, but if you want a detailed explanation, uh, uh, if we explain here, we will not be able to cover a lot of the topics. But there are some very good explanation in the pre-read videos, which has been released, and within the, I think Andrew Ng's lecture videos, the first 2-3 videos talk about the details of the operation, like the how this actually does the edge detection and all that by finding the gradient. So this is actually a representation of the discrete gradient operator. So
So imagine this particular kernel that he's showing, that Sumandeep is showing, right? Which has -1, -2, and -1 in the left column, and +1, +2, and +1 in the right column. Imagine it is put on a 3 by 3 location in the image, and left side are low pixel values, that means darker values, and right side are brighter values. Then if you put this kernel on top of that, it will give you a high response, right? So let's say you have 0, 0, 0 on the left hand side and 255,
right,
255.
you can see this region
Yeah.
back end of the hat,
Hmm.
where the background is dark and the hat is bright, and we end up with this edge over here.
Yeah. So it
So
is
it,
looking for a matched shape to its own change in numbers as you go from left to right and top to bottom.
Hello,
Yeah.
sir. So basically, where the pixel difference is more when we're going from left to right, so it taking it as a edge.
Yes. So
yes,
wherever there is a sudden change in pixel values when you go from left to right and the change is positive, it will give you a very high response. It will give you a very high cross correlation between that 3 by 3 portion of the image and the 3 by 3 kernel. Clear?
Yes, sir.
So basically that's what kernels are doing. They are finding their own shape in the image or in whatever feature map they're applied to in
like
different
this Laplacian thing, right? So it's actually looking for points which are significantly different from the surrounding areas. So it's like multiplying every pixel with 8 and subtracting the region. So if it's smooth, like if all the pixels in the surrounding have similar values, the total sum of these boundary 8 pixels, right, will be -8. So the weighted summation, it will get cancelled out. So the regions which are smooth with uniform values in the region, they appear to be black in the output. And the region where there is very rapid change in the surroundings, there this -8 does not get cancelled with the +8 at the center pixel, and there we actually get like a strong response. So it is able to detect regions where a lot of activity is going on, a lot of change, and anywhere where the like in this region it's like smooth, so the output here is like mostly black. So it's different logic, like different numbers basically tend to showcase different like logic. And all right,
Kasina,
we'll
you had a
move.
question? Sorry, there are
We'll,
still questions. Yeah. Kasina, you had a
Yes,
question?
sir. Yeah, could you please go to the previous slide you were showing uh, about
which
the
one? This
last?
one?
No, no, the last filter which you spoke about. This, yeah, this one. So, if after this, yeah, no, uh,
Next slide. Next slide.
uh, Laplacian HPF.
Right.
Yeah. So, can I say if the mid value, which is 8 here, if I increase that, I would get more brighter, where the features are distinct, I would get more uh, brightness there. Can we say something like that?
Where there is a lot of change, there is a lot
Yeah,
of
where there
local
is a lot
change
of
in the
change,
region, there you
like in
will
the
get more
hat.
bright. Like you, the entire hair, right? The
Yeah,
person, this not hair, this some kind of a decorative like false hair kind of thing on the hat. That's all bright, and wherever the rim of the hat and the boundary of the hat, it's all bright because there is a change in that region from the surrounding regions. But wherever the the background, it's mostly smooth, like there are large regions of same color within that, there you don't get much of response, right?
yeah, thanks.
Right.
So another question, I think people are still a little confused about stride.
Stride,
So
I'm yet to come to stride,
I
so
see. Okay.
yeah, yeah. So stride is like, so in the valid convolution and same convolution that we saw before, we were putting the kernel in all possible positions. Like in this, without padding, we were putting it on all possible positions within the image. Here also we were doing in the all possible positions. But what if we skip some positions? So here in this example, we do the same valid convolution but with a stride of 2. That means first we put it on, say, left top corner, and then when we have to move it to the right, we don't just move it 1 pixel, but we are moving it 2 pixels. And similarly, when we have to scan the lower area of the image and we have to like shift it down, we don't shift it by 1 pixel, but we shift it by 2 pixels. So by doing that, we reduce the number of positions where we look for the filter. So this is a technique to reduce, if you want to reduce the size of the output. uh, and also the reasoning comes that because anyway we are not missing any location, uh, because different positions within the image, they get covered by at least one filter or the other. And so there is a logic. If you want to reduce the size of the output, we use strides, especially where we have big filters. Usage of strides is common when we have bigger filters, not just 3 by 3, but if in case we are using large filters like 7 by 7, 9 or 11. And so in that case, usage of stride is more common. Usually with 3 by 3 in practical applications, we don't use stride. But for this example, just to visualize the stride operation, I have used a 3 by 3 filter and use a stride of 2. And here is the derivation of that. You can just find out number of possible positions, and this is a quick arithmetic. If you do, is the derivation. So the n plus 2p minus f we have already find out using the size of the image, filter, and the padding. And by doing this stride, what happens is the number of positions, right, uh, gets divided by the stride. So if the stride was 1, we do all the position. If stride is 2, the number of positions are halved, and so on.
Sumandeep,
Right.
just suggestion. Look at the Google pointer tab on the left down. When you hover, there is a Google. Yeah, there's a
Oh, is
pointer
a
option.
pointer tab? Oh, okay, okay,
Yeah.
okay. Oh, this is nice. Right. So yeah, this is the formula. Yeah. So this is the formula. Okay. And
Sumandeep, if you want to skip some complex convolution concepts, you can do so. We can cover it tomorrow also, like dilated, for example.
yeah, I just introduced it for completeness. I'm not discussing it a
Okay.
lot. So
Because
when we
tomorrow
are
for
discussing
segmentation,
strides, so I
I'll
thought,
discuss it in
put
this.
that as well. Although it came much later, the concept of dilated convolution in CNN and all that. So it's just something similar to strides, but in a different manner. It's like instead of skipping pixels from one filter position to another, within the filter positions, it introduces gaps. So for a 3 by 3 filter, we need to look at 3 by 3. So basically 9 pixels, but uh, instead of looking at contiguous block of 3 by 3 pixels, we just use a gap and look at a much larger. So it has an effect of uh, applying a larger filter by utilizing a much smaller filter. This does not find much application in classification application, but this does have an application, especially in pixel operations like segmentation and all that. I think it may be covered in a later course. Okay, so we'll move on to the critical concepts before we introduce convolution neural network. One of the concept is multi-channel convolution. That means that previously we just saw input image as just one array, 2D array of values. But when we have color images per se, there are three different layers of an image, that RGB, right? So every colored pixel is represented by three numbers, which is the composition of the primary colors. And so the input itself is like NH into NW into NC, or in this particular example, 6 by 6 cos 3. So when we have to apply a filter on it, we have to define the filter weights separately for the red channel, green channel, and blue channel. Because what we want to do with the red color of the image may be different from what we want to do with the green color or blue color of the image. So the actual filter what we define is F cross NC. So we end up, in this case, we end up with a 3 cos 3 cos 3 filter. That means there are 27 coefficients. And to compute the output is pretty simple. We basically apply the three different filters to the channels separately, and we compute the weighted summation of each of the filter, and then add up the output of all the three filters into the output, right? So here is an animation I've put to describe the whole process. So when we are processing color images, we have three channels, so basically three kernel filters, and the values of the kernel may be different for the three channels based on our whatever application area we have. And so what we do is independently apply each of the channel on each of the filters on each of the channel, and compute the values for each channel, and then do a total summation of it and put in the place. So although the input was three channel and the filter was three channel, the output is still one channel. All right. Then we extend the concept to what if we apply two different filters to the same image. And when we talk about two different filters, that means each set of filter which applies on each channel. So here we have filter one on the top, which applies on this input image, and we generate this output. That means, so the three layers of the input image, three color layers, get collapsed into one layer of output. Similarly, a different filter, we choose a different filter and apply it. So apply it on the same image, and we get this output. And the final output is a stack of outputs. So in this case, we have two filters. So we ended up with an output as 4 by 4 into 2. This 2 is the number of filters we apply, like one filter and two filter. So each filter applying on RGB and doing a weighted summation, not only across the 3 cross 3 space, but also across the channels. So basically it does a weighted summation of the 27 numbers, and it computes one thing. and with a very different set of coefficients of filter, we can compute another thing. And so we can, generalize this concept, and we have, let's say we have nf number of filters, and so we will end up with output as like nh dash nw dash based on whatever. In this case we are using like stride 1 and padding is equal to 0, so we are ended up with 4 by 4. So whatever this nh dash nw dash we choose, but the number of outputs will be equal to the number of filters that we apply. Size of the filter, yeah. So all these things, I'll discuss all the hyperparameters together in one place when I've introduced all these concepts. So all of these are hyperparameters like size of the filters, number of filters, padding, stride. Uh, there are even more hyperparameters which will be introduced in the further slides. So these are all hyperparameters, but the values within the filter, like these 27 values for filter 1 and these 27 values for filter 2, these are our learnable parameters, which will be determined by uh, the data we have and the output we expect from the data. So we'll learn these values, and we'll start with some random initialized filter values, and then using the same concept that we have learned in deeply dense neural networks, like using gradient descent and the similar algorithms, we will learn to find out the right filter coefficients for the uh, purpose we have. So yeah, there is a question. So this is a stack. So we have NF filters, and the output is another stack of NF layers. Right. So now we have a grasp of the basic operations in the. There are questions like how do we convert a color image in black and white? So colored image to black and white, you can convert using like simple equation is like, replace the output as R plus G plus B by 3. That would also work. But based on the sensitivity of the human retina, the more relevant equation would be like zero point 0.3 into R plus 0.6 into G plus zero point 0.1 into B by 1. So these things you can just quickly search. Most of these concepts were very well explained in the literature. I mean, even in Wikipedia, you will get these things on why the reason, because we are more sensitive to green, and we sensitive green color more and more. So when we convert it to grayscale, question. We do have conv 3D here, but we use the same filter with copied elements. No. So because we may want to, it depends. In certain application, we may want to do the same operation on all the 3 color channels. In that case, maybe the data will automatically train the weights to be same. But in many applications, we want to do different things. Like, for example, we want to have a filter to detect human face. Now, the skin color is a tone of red. So, of course, if you find reddish tones, right, reddish or pinkish tones in the input image, that has more importance than we see blue. If the blue is prominent, then probably it's not a human face. So we don't copy the same filter for the 3 channels.
So the idea of a filter is the following, right? So first of all, your image size, the height and width can be much larger, right? But your filter size is very, very small. It's like 3 by 3, 5 by 5, 7 by 7, etc. Right? So very small. So point is that it is trying to look for a a shape that matches to itself in a small window of the image. What is the logic behind that? The logic behind that is, let's say you're looking for an eye of an animal, right? That eye can be anywhere in the image. So I don't need to build an eye detector that a separate eye detector for each location of the image. I just build an eye detector and apply it at different locations in the image. So that applying at different locations is the stride, right? So you're shifting right by one, shifting down by one.
These concepts are explained just few slides down the line.
Right.
Yeah.
So why it is not a 3D convolution in RGB case is because you are not sliding from red channel to green channel to blue channel to find something. Although if you had an MRI, right, you have different slices, right? So you have the depth channel. In that case, you're looking for the same edge in the top slice, the second slice, or third slice, and the bottom slice. So then you are convolving in the third dimension, but not in red, green, and blue. All right, go ahead.
Another question, stride can be greater than filter dimension. Yes, you could, but then you will skip over certain pixels altogether. So, so say at one position you apply the filter and you jump over larger than the dimension of the filter, that then you have missed some values altogether. So may or may not be useful in your application. I mean,
Yeah, I have never seen that.
yeah,
Usually it is
generally
left and right.
it won't be much practical, right? Better to remove those data from the input image and then go through the processing. Like, why have those data if you're not going to use them? So you can actually remove those rows and columns and reduce the size of the image and probably do that. So okay, so here whatever the operation we learned in the previous slide, we put together in one place. So and we put it in the form which is familiar. Now it's familiar what you have learned in dense neural networks. So we have an input image which is nh into nw into nc, and we have a set of nf filters which we apply, and so each of the filter is of size f cross f. And for simplicity, when we are implementing convolutional neural network within one layer, we generally do not tend to use filters of different sizes, but there are some applications. We'll discuss it later in the class today. Okay, so we have nf number of filters, and we call the coefficients of all of that combined as like W, which is the weight matrix. So these are all different values. So NF filter. So each filters contains unique f into nc number of values. So the total number of coefficients in this layer is nf into f into f into nc. And then we also have a set of bias values, so which is basically a fixed shift, a constant shift with whatever the weighted summation we compute using the filters. So we have nf number of bias, that means one value for each filter. So it does not differentiate between channels, but whatever the output of each filter, we can have a bias. So we define a bias variable. So these are also learnable parameters which the data and the algorithm will learn from the data. Okay, then so the output of each filter is nh dash into nw dash, which is anyway dictated by the amount of padding and the size of filter and the stride we have chosen. And then the output of the filter, right? We pass it through a pixel-wise activation function. So this, say for this particular first filter, we get an output from the convolution operation as nh dash into nw. That means there are nh dash into nw dash number of pixels. Then we have a nonlinear activation function of our choice, which is applied to every pixel independently. So the output is the same size as the input before the activation, but now the output is processed via a nonlinear activation function. So why non-linear activation functions? So the entire operations, right? The filtering operations is a weighted summation, which is a linear operation. Adding of the bias is a linear operation. So if we don't have a non-linear step, then multiple layers effectively would get collapsed into one. So I think somebody asked that questions earlier, like the when we showed the two-stage filter, right? First applying like Laplacian of Gaussian. So apply the Gaussian filter followed by Laplacian. So when we do that kind of operation without a nonlinear stage, effectively we can come up with a very different filter which has the same effect. Uh, but if we do that, then multiple layers will have no use. So to actually model the complexities within the input data, we have to introduce non-linearity, this thing. The same reason it is also used in the dense neural networks as well. So F activation must be a nonlinear function. So the final output is a stack of NF layers. Uh, yeah. So the final output of the whole convolution plus activation step is NH dash cross NW dash into NF. And funny thing is, like, this NC, right? For the input image, if it's a color image, then it's 3-channel. And then the structure of the output is very similar to what it was in input, right? Different dimensions, but the whole concept is similar. So when we apply a second layer, the NH dash becomes NH for the second layer, NW dash becomes NW for the second layer, and NF actually becomes NC for the next layer. So the next layer, and in this case, if there is maybe 10 filters, it appears to the second layer. It's an image with 10 channels, right? There are some questions. Video is same as image number. Okay. I think we can answer these things later in the class. It's not related to the content. If there is time, I will explain these things as well. Yeah. So the choice of activation functions, I think this was, covered in dense neural network as well, but we introduce here. Because earlier in the state of the art, sigmoid and tanh were the most common functions. Then around 2010, ReLU, leaky ReLU, these got introduced, which are now the more widely used activation functions, and all of these are nonlinear. That means the output is different from the input, and we will see further usage of that. Okay, let's now introduce a new concept, which is different. It's a layer, pooling layer. So pooling, as the name suggests, right? We pool a mix of numbers, and pick one of them. So how do we pick one? Is like okay, let's explain the average pooling first, because it came first. So in the literature, about 20 years back, average pooling was the de facto thing which was used. What it basically does is like, if you apply this filter, it's kind of filter. What it does is does a weighted summation, not a, it's just as a simple summation, and computes the average value within its region and outputs it. So we apply the filter over here. The average of 2, 3, 4, and 7 is 4, and 1, 9, 3, 5 is 4.5, and so on. So in this case, we are applying this average pool as a 2x2 filter with a stride of 2. So there is no overlap. In this particular application, there could be an application where you could have overlap, but here the 4x4 input without any overlap, we convert into a 2x2. So what it does effectively does is selects the average of incoming features. So what we are doing here is at every stage we are computing a set of features, right? And to reduce, sometimes it is helpful to reduce the data in the subsequent step, because every time we are increasing, right? If there are, like, in the first stage there were 3 channels, and if we select 10 filters, then we end up with 10 different values and all that. And there have to be a method of decreasing the amount of data to control the increase in amount of data. So average pooling does that. Selects an average, basically, mixes up the incoming features and computes the resultant features. But later research found that it is actually more helpful to use the max operation. That means uh, there are incoming 4 neurons and it proposes 4 values. We are better off choosing the most important feature. So max pooling became the more de facto standard because it tends to work better in that sense. And we are interested in the most important feature, right? Because features, the areas of the image where we have not detected a significant feature what we are looking for is not much of use to us. So um, this is what it does. And what effectively a pooling layer does is the enlarges the receptive field of subsequent layers. So here a 2 by 2 pixels in the input layer meant 2 by 2, but here after we have done the max pooling, a 2 by 2 region effectively represents a 4 by 4 region from the previous layer. And what it helps us build the structures, right? So as we talked about before, right, the earlier layers does very simple operations like detecting the edges or corners or blobs, this kind of thing. And slowly we want to build responses which combine smaller parts to make larger parts. And so, like, if you have a human face, we are trying to classify person or not a person. So the pixels within the edges or the curves, changes in shade within the person's eyes slowly will build up the structure of the eye. And then slowly the 2 eyes and nose will start to build up the structure. So there is a hierarchical thing going on. And so with every passing layer, we need the responses to effectively represent larger and larger areas within the input image. Any questions on the pooling? Uh, Hello?
Yeah, I had one question
Yes.
about ReLU. Whenever they talk about non-linear ReLU, they just means regular ReLU function?
Yeah. So ReLU is by far the most used. There are
Okay.
some papers which have used leaky ReLU. So
Okay.
leaky ReLU is, in most cases, ReLU is good enough. Leaky
Mhm.
ReLU has some advantages. Uh,
Okay.
so yeah.
Okay. Thank you.
And deep learning community in convolution neural network now is exclusively in the ReLU, like ReLU or leaky ReLU, it's there. 2010, I think, paper by, I think the AlexNet paper proposed this, Geoffrey
A-
Hinton and Alex Krasovsky.
And just to be clear, because of no saturation is the reason we are going for ReLU.
No, not actually. Yeah, saturation in that case, yeah, sorry. Saturation in that case is that like the gradient does not become like close to like sigmoid and tanh.
Mm-hmm.
Like the gradient here, I mean, this is a very bad diagram. I mean, it's become almost flat. But
Okay.
yeah, here the gradient is not zero, but almost zero.
Got it. Got it.
And when we actually do deep learning, so the effect of that what becomes is very deep. When we do back propagation, the effect of the gradient becomes very small.
Okay. Okay. Okay.
So we don't want that. So we want responses. So ReLU never, gradient, as long as it says positive, that positive means, you have a positive feature.
Got
So
it. Got it.
the gradient never goes down. I mean, gradient is always one. So
And yeah. And one
response,
more
the
question.
gradient response is carried back web propagation. Yeah.
And whenever you say feature, is it a number, a numeric number?
Yeah, it's a number, right? We are
Okay.
dealing with number, like in edge, right? We
Mm-hmm.
when we applied the Sobel edge filter, so the
Mm-hmm.
output was a number. So when we
Mm-hmm.
say prominent feature, that means the Sobel operator generated a very high value, like close to white.
Okay,
And if
okay,
it is
okay, okay.
black, that means low value. That means it's not an important feature. So if we are
Got
only
it.
interested in edge detection, then
Uh-huh.
the regions of this image where there will be high values will be
Okay.
interested only on those values of those locations, right?
Okay, okay, okay.
Right. So output of the filter, if it's close to zero, that means the filter, whatever it computed or tried to compute, is not present in that region of the image.
Okay,
If
okay,
it
okay.
computed a value which is high, which is close to white or 255,
Okay.
we say it's an important feature. That means whatever we were looking for, we found
Mm-hmm.
that in that region of the
Okay, okay.
right. So that is why that is the reason, kind of that max pooling turned out to be kind of better. Average pooling
Mm-hmm.
still has some usage. I mean,
Mm-hmm.
as recent as 2014-15, some papers have used average pooling,
Mm-hmm.
very famous and prominent one, but for a
Mm-hmm.
specific application, which is it's purely reduction, like purely reduction of the amount of data, like increase of
Oh,
receptive field, and so it's not trying to pick up the prominent features, but purely for a like reduction of the data. So as a stage which reduces the amount of data, average pooling is still useful. But for most applications where we are more interested in the like the important features, pick up the important features from every stage of computation, max pool is still the most widely used
okay.
right.
Thank you. Thank you very much. Yeah.
So we add the pooling layers to the convolution layers. So here, whatever conv we have represented is the whole thing, right? The W operation, W matrix multiplication with the, which is the filter, weighted filter with the input, plus the bias and passing through the activation function. So that's the whole process which we define here in this diagram. This is the whole conv block. So input is NH NWNC, output is NH dash NW dash NF. This whole thing is represented as the con block. So we present actually the first ever like convolutional neural network paper, which came out in 1998. This was the first paper with a full proper convolutional neural network as a solution to a problem. And this is just 5-layer mm, network, which contains like why we call 5, although you can see a lot of layers, is so okay, one more important thing, right? Max pooling has no learnable parameters. It is just a functional operator. It is still a filter in a sense. It has a filter size, it has stride. uh, there may also be padding involved in certain applications of max pooling, but it has no learnable parameters. It's just a max operation of a region. So it has hyperparameters, which are the size of the filter, padding, stride, whether we want to choose max or average. So these are still hyperparameters, but there are no learnable parameters in max pooling. So uh, the standard like the practice is that whenever we are describing a network and we are counting the number of layers, we generally tend to count only the number of layers which has learnable parameters, right? So we just discussed the structure. So this LeNet 5 was actually proposed for document recognition. The primary application area was like pin code recognition in letters. It tried to solve the problem of uh, like digit recognition, handwritten digit recognition. So and at that time in 1998, given the compute power and all that, it could work only on a very low resolution image of 32 cross 32 cross 1. That means only a grayscale image, no color, where uh, um, like there is letter on a plain sheet of paper, right? Number. So it started with a 32 cross 32 cross 1, and then the first layer was 5 cross 5 uh, convolution. 6 such filters was used. So for the first stage, NF was 6, and the padding was 0, and the stride was used was 1. So because of 5 by 5, we lost 2 pixels on around the boundary. So total reduction is 4 cross 4. So we end up with 28 cross 28 cross 6. So it's a stack of 28 cross 28 outputs, a stack of 6 filters. And then it used TANH activation for the internal layers. And then we have an average pooling step with a filter of size 2 and stride is equal to 2. So it basically, halves the input image only along the NH and NW. So it only affects average pooling, any kind of pooling basically. It applies independently on each channel. So it does not have any effect on the number of channels of the output. So the output here became 14 cross 14 into 6. Then another conv layer with another 5 by 5 filter with padding 0 and stride is equal to 1. We again lose 4 pixels on the boundary, and the output becomes 10 cross 10. But in this second stage, we used, like in this paper, they used 16 filters. So the output becomes 10 cross 10 cross 16. Another stage of average pooling, we halve the number of width and height, and we end up with 5 cross 5 cross 16, which is equal to 400 so values. So we end up with a kind of a 3D volume of 5 cross 5 cross 16 with 400 volumes. After that stage, what this paper proposed, and which is the similar architecture is still common today, is what the convolution steps did was, the 2 stages of convolution and average pooling did was compute 400 features. Ultimately, we computed 400 features, and now these features are going to be fed into a traditional neural network, dense neural network, which would act as the classifier. So this is the like architecture proposed here, and the structure has more or less remained the same even now. So that is why this is a very like seminal paper. So the input to the fully connected layer is 400, and there are 120 units. So the number of like connections in this stage would be 400 cross 120. Connections, and then the 120 outputs are further connected to another layer of 84 units, and then the 84 units are connected to another layer of 10 units, which is the softmax 10 levels, because we are doing digit recognition, so it's 0 to 9, and that is what we get. So there is a question from my side is, as we see that, when we slowly apply, different layers of filters, the NH and NW after each layer goes down and NC goes up, right? And I will answer that. So I think NH, NW, I have already answered that in the earlier, that with every passing layer, we want to build upon the like we want to build upon the like the small features, like edges and like very simple features like edges, corners, and blobs, and slowly start building bigger and bigger structures. So effectively, NH and NW, smaller value of NH and NW in the later stages, so same pixels effectively represent larger areas within the input image. So here, 1 pixel would effectively represent probably, so it's got 10 by 10 and it's 32 by 32. So it's like 3 by 3. So 9 pixels here would kind of end up with like effectively compute the value of 1 pixel over here. So this way, the representations and the later layers uh, basically derive upon the information from larger and larger regions within the image. Why NC goes up? Like in the previous stage, we only used 6 filters, and in the later stage, right. So in the later stage, we have more filters. That means so number of basic filters, right? The basic shapes, basic constituent shapes are less. Whether I'm representing a human face or a dog's face or a car, the basic geometric face shapes in the world are very limited, like the edge, corner, or a curve. Or so that is why the earlier layers are detecting only basic shapes. So less number of filters are fine for that purpose. But as we go along and start building more and more complex shapes using the basic shapes, the variety of complex shapes that could be there increases. So to successfully represent that, we need like more filters. That means different filters end up different shapes. So if you're trying to build, say, the shape of a car from edges, then the part like part of the edge of the window or the edge of the bonnet or the edge of the rear view mirror, how they look, they are much more varied than the basic geometric shapes which build up those. So this is the kind of the analogy here. You can assume that that is why we need more and more filters as we go along the depth of the uh, network. So this was a very simple network back in like 1998. TANH was most common activation filter at the time. Average pooling was common. There was still no concept of max pooling or other such things which will get introduced later on. And very simple network with just 61,000 parameters. And out of the 61,000 parameters, most of the parameters are still in the fully connected layer. So, but it works pretty well. We'll see it in our hands-on like case study a little bit later on. Okay, so this is from the what we saw from the LeNet 5 example, and this is, you can assume, as a like a generic template for a complete convolution network. That we have an input image, and there are L1 convolutional units. When we say convolutional unit, it involves one convolutional filter followed by some kind of activation, followed by some kind of pooling. So this scheme repeats, L1 number of times. Like in this, it repeats. In the previous, it repeats twice, and then followed by L2 number of fully connected layers, which also in this example repeats twice, and then followed by a softmax layer. So if it's a 2-class problem, it's basically your logit function. If it's a multi-class problem, it's a sigmoid function. So usually, but the convolutional steps, however number of convolutional units are there, what they are effectively doing is doing the feature detector, which before the basically, before the invention of convolutional neural networks, or basically the formulation of convolutional neural networks, were done manually by engineers, or mathematicians with experience into, signal processing and the knowledge of the problem. So they used to manually create those filters and basically detect features and have feature transformation functions which would compute the features. And then the rest of the machine learning still was there. So machine learning has been used for a long time in computer vision, but not convolution. So convolution neural network, the first time where using data-driven approach, you were able to learn the feature detector. So you did not need to have a deep mathematical understanding of the domain to actually develop the features. So is there a question on the chat? Yeah, I think that is so. So that is the thing. So you can assume that the set of repeated convolutional units, that a whole thing is actually a feature detector, and the whole fully connected layer is a classifier. And there have been a lot of different combinations. So why fully connected layers? They have people even have tried convolutional feature detectors, connected with say support vector machines as a classifier, and that also works. Like there are some applications, some papers which have done this kind of stuff and works. They have some success in those. So so the classifier technically could be independent from the feature detection. Okay, let's move on. Yeah, so here's the whole collection of hyperparameters that we could have in a classic convolution network. Classic, when I say, is which follows the pattern of the LeNet, and many of the even the latest algorithms which are getting proposed more or less follows this template. So the hyperparameters are NH and WNC. Why? Because sometimes we want to design the network for a particular size of image, and whatever the input image is, we first use simple image processing to resize the input image to the required image size of our own design network. And so that is still that is also kind of an hyperparameters. Number of channels, again, do we want to go with color images or grayscale images? That is also kind of an hyperparameter. Then how many convolutional units we want, that is the biggest hyperparameter. So it depends, it dictates the whole depth of our feature detector. And within each layer, so these F, P, S, NF, FP, SP, all of these are could be different for every layer of the L1 units. So there is number of filters for each filter. There's padding, stride, and the number of filters in each layer. And then for the pooling step, we must decide what should be the size of the pooling filter and what should be the correct stride of the pooling filter. Very common approach is to use SP is equal to FP, so that there is no overlap, but other variations also exist. Then comes the how many number of fully connected layers. So how that is the classifier part of your network. So how many, so depends, right? Whatever features you have computed, right? Depends if your how complex is your problem, right? In dense neural networks, you might have seen, like, if the data is very nonlinear and non-separable in nature, then you need more and more hidden layers. So depending on that, you decide on number of fully connected layers and choose the number of nodes in each layer. So this NU is not one NU, but NU is different from each for each of the L2 layers, right? Right. There is a question. I think Professor Sethi has answered it. Yeah. So yeah, I mean, for visualization, we have used that diagram, but things are not simple. If like explainability in convolutional neural networks is still a bit of a challenge. Okay. So now we have learned what the convolution is, and we had in previous module learned about the dense neural networks. So why convolutional neural networks are suited to computer vision? And these are the primary two reasons. One is parameter sharing. Parameter sharing means, if you're trying to detect a person's face, right? Whether the person's face is in one part of the image or another part of the image, it looks same. So why learn different parameters? So if we consider the whole image as one massive input vector, then we will actually end up learning not only how a person face looks, but actually where kind of we will overfit on the locations where the faces appear in the image. But to describe an image, describe a face within an image, right? The parameters the features, right? They remain same irrespective of where in the image the face appears. So each filter, it detects a different features, and whatever feature we are looking for in one part of the image, the same values of the filter, right, is good enough to detect the same part in another part of the image. So why learn so many parameters which are not needed? So it reduces redundancy in the number of parameters. So lot less computations, right? We will see in a later lecture where we compute the number of parameters um, uh, uh, like for each convolution step, and you'll see that the convolution that does not generate a lot of parameters. And second thing is sparsity of connections. Is like when we are trying to define, say, a dog's ear, right? So the dog's ear uh, does not depend on the whole content in the whole image, but only within the pixels, local group of pixels which constitutes the dog's ears. And so relevant content, is contained or is only in a part of the image and does not span the whole image. So when we are trying to detect parts to build up our shape, whatever we want to finally classify, uh, each part is only dependent on few pixels. So it does not make sense to have a network which takes in all the data of all the pixels just to find the like uh, like say the ear of a dog or the eye of a human in a classifier. So and this also provides robustness to localization. So no matter where the ear is, it will still get detected properly. It has nothing to do with any other pixels which may be far away from that location. So these are the two primary things. One, we get a lot of reduced computations and with a lot of reduced parameters due to parameter sharing. And we also basically introduce robustness, which actually has a effect of regularization and prevention of overfitting. So if we use dense neural networks for computer vision applications, it tends to overfit. You will get very good, even with very few layers, you'll get very good training results, but they may not generalize well to previously unseen input data. Okay, now we revisit that whole thing. So we have shown this slide before. So now you understand somewhat, what the earlier layers doing, middle layers doing, what is the output. But this is a very simplified view of what is actually happening. So it's not that easy, like to actually find. So if this is a car detector, it's very difficult to actually, or not possible to locate a particular filter which detects the tire, because the way we interpret the image, right, in our human understanding is very different from how the algorithm represents. So it actually may not strictly, look the tire as an abstract shape, but could actually look at some other combination as an abstract shape. So our understanding of the parts which we use to assemble the car may not correspond to the parts of the object within the image that the algorithm learns and builds up its own understanding of what the object is. So there is this gap, and there has been research, and there are some way we can visualize some things and try to explain it, but there is, I think, still a bit of gap in explainability of what convolutional layers, how exactly are doing and what exactly they are doing. We can just visualize the output, but it may not make much sense. Like this thing may not make much sense to a human, but for the numbers it does. If there are any questions, then I will. Okay, yeah, this is another thing. So this is a kind of a visualization. Again, I mean, this is also like a kind of representation visualization. So it's like this, right? The same concept, like the earlier layers, this is a representation of the Google Limit, which we will look up much more closely towards the end of this lecture. So like the earlier layers is detecting different types of edges, and the edges slowly build upon textures. So the middle one, like early middle layers detect texture, different type of textures available within the image, and the textures slowly build make up patterns, and the patterns make up parts, and the parts makes objects. This is still a visualization of what may be happening, but yeah, I mean, but it may not be exactly how happening how humans interpret the parts of an object, right? So um, this kind of is clears it a bit conceptually, but it may not match up with humans' perspective of what it is doing. That is still an area under research. All right. So now we are done with the theory of like classic networks. And now we'll move on to use case. So we'll apply the Lenet 5 model that we have like how much time? Okay. So we apply this model to the MNIST problem, which is a handwritten character recognition, digit recognition, which was the original problem for which the Lenet paper was proposed. So these are the kind of response we get. So the hands-on coding thing, how to code up the Lenet in TensorFlow and all that, I'll be going through that during the tutorial. Here I'll discuss the conceptual aspects of the algorithm. So the in the tutorial I'll be discussing how to code like your convolutional different types of convolutional neural network within the like using TensorFlow, and like how to observe, like how to plot these training and validation, and how to check whether there is overfitting, underfitting. These all concepts. The coding aspect of it I will discuss more. I will release the notebooks, and I will explain all those things in more detail during the tutorial, which is I think on Thursday. But here I will conceptually explain what happens in this MNIST dataset. So when we try to train it, the Lenet 5 model with MNIST dataset, which is like 60,000 images, that means 6,000 for each character. We get very good training accuracy, which is 99%, and the validation accuracy is only okay. There's a question backprop. So backprop is same. The concept of backprop is same as the dense neural network. That is why I have not covered it. Okay, I'll just visit it quickly. So here we are representing, right? W is a matrix operation, right? So effectively the filter is nothing but a weighted summation, which is basically a matrix operation. So the outputs here, right? Basically you have weights which are like f cross nc number of weights into nf number of weights, and you have this the input vector is three-dimensional, but you can assume it to be a flattened single dimensional, and these weights whichever applies to whichever like image location. So you will end up with a linear equation of weighted summation of here you'll end up with a linear equation of weighted summation of all the input pixels and the weights and the biases, and then passed with an activation function. You will end up with another function. So the backprop works exactly the same way in this. The derivation for the backprop for convolution in itself is like could take a couple of hours to explain. So that is covered in the pre-read videos and is explained very well by Andrew Ng, and So you can go through that, like, but that's a very long discussion to actually derive the backprop equation. But the concept is similar because it's a linear equation followed by a nonlinear activation function. So you first find the derivative of the activation function, and then the same using the chain rule, you compute the derivative for each of the weights of this. So the number of weights here are nf into f into f into nc. So for each of the weights, you compute your derivative using chain rule, and then you update each of the weights after each step of the backprop.
Were all the 60,000 images manually annotated in the MNIST data set?
Yes, yes. I mean,
Okay.
it was created in, I think, like in 98. And
Okay,
then
okay.
later it became such a standard that it is now included as a standard import library, like some standard import data in almost all of frameworks. It's like the hello world of like
Okay, okay.
like
And also,
any kind of image processing algorithm, machine learning.
okay,
Yeah.
okay. And also later on, will you also talk about this annotation technique where you make automate it instead of manually doing it later on in the course
Auto
somewhere?
annotation.
Yeah, because let's say,
Not in this module. I maybe discussed in some later module. I'm not sure.
okay, okay, okay,
Not today. It's a much advanced topic. So okay. So we'll just discuss the case studies and move on to the later more complex architectures over LNF.
okay, okay, okay.
So
Thank you.
here we can see, here I want to conceptually discuss this, how to arrive at this and the coding and aspect of it. I will release the notebooks just after this lecture, and you can have it, you can try it out, and I will explain the code during the tutorial. So so the model is a good fit, right? We have a very good training accuracy, and the validation accuracy is also close enough. So this is a good fit, and the validation loss is also very much following the training loss. So it's a very good model. So and it is expected because this is the problem for which this original paper published this network. So it's a pretty good thing. Then, of course, the MNIST, simple MNIST is a very simple data set. It does not have much more complexity. It's a very basic data and does not showcase the full power or capabilities of convolution neural networks, or is not representative of more complex uh, use cases. So there is another data set which was created sometime later, was called Fashion MNIST, which is basically does the same thing for fashion data. It still uses the same size, 28 cross 28 grayscale images to represent 10 different types of clothing items, like t-shirt, a trouser, a pullover, dress, coat, sandals, shirt, sneaker, bag, ankle boot, stuff like that. And it's got the same number of images and same resolution, but of course the objects are much more complex. Now we try to solve the problem using the same linet. We get good results, but do run up into some problems. The training accuracy is good, like after 200 epochs it has become like reached 95%. The validation accuracy is not excellent, but good enough at around 90. But what happens is, the validation loss is, tending to diverge from the training loss, and that is a symptom of overfitting. So, which basically is that the model is not a very good model. Like on training, it is good. Validation also, it's reasonably good with 90% results and all that. But there is still a tendency of overfitting. And overfitting is primarily because the variations, right? The shapes in clothing and shapes and patterns in clothing are really a lot. So say in this training set, they have just have like 6,000 images for each type, but in reality, The number of variations in clothing is in millions. So what happens is the data is sparse, and that is why the model tends to overfit it. And we will discuss some techniques how to mitigate that just after a few slides. Okay, and then there is another data set which is even more complex problem, which is a CFAR10 data set, which and again has 10 classes of like objects and animals as a mixed set of objects and animals, and it's got 50,000 training set. That means 5,000 images of every set, but the complexity of the objects, right? It's much more, way more complex, and also it is 3-channel color, so color variations also come into play. And when we try to build a network with LeNet, it completely fails. Training accuracy reaches 90% after like 600 iterations. So it's slow to train, but does reach 90. And I presume if I keep it running for tens of thousands of iterations, it'll probably reach, the way the curve is going, it'll probably reach 99% accuracy. But the validation accuracy never moves beyond 55. And even more worrying is that after a certain number of iterations, the validation loss hugely diverges and even becomes worse as we keep training it. So it's a like extreme overfitting is happening because, of course, 5,000 images per class is no way close enough to represent the variations possible, say in cars, right? If you pick up the automobile class, considering different shapes and brands and types of cars and colors of cars, and different poses, right? From which direction the car has been photographed, the number of possibilities is really, really large. So this kind of network overfits it, so it does not work well for these problems. So the techniques, right? When in computer vision, we commonly run up with this problem that we want to solve a problem. And of course, with internet and a lot of camera devices, there is a lot of data in the domain, like, but the data is not, annotated, or annotating and collecting and curating data is a very expensive, cost wise, time wise, energy wise, a very long process. And so although we have like billions of images on the internet, the actual whenever we want to solve a problem, the relevant proper images with annotations, curation is less. So computer vision, insufficient data is a very common problem, and that is one of the causes of overfitting of networks if we try to train it with insufficient variation in the data. So the training data cannot represent all the potential variation. It only has limited examples of the data. So it learns only those examples, and anything that comes which does not fit that pre-existing notion, the network fails. Gathering data is expensive, takes time, money, and it's a tedious task. So what we can do here, and it is a very, very useful thing, fortunately for computer vision, is we can simulate the variations in data. It is more easy to simulate variations in computer vision than in most other applications. So what we do is, using basic image processing techniques, modify the training data and add to the training. So data augmentation is just that. So say in the training set, we only have this cat image, okay? And we can synthetically generate more cat samples, which are still cat. And it would be very difficult to actually have a cat and take so many pictures. So what we do is, take one picture of a cat and we annotate it as cat. We annotate just one image and synthetically, generate more images of cat, which could represent different variations of how the cat would look like by mirroring, which is like horizontal flip, vertical flip, zooming, like on the right corner we have zooming, so we are zoomed into only the face of the cat. So face of the cat is still a cat, full cat is a cat, the face of the cat is still a cat. So when we are doing classification, we can get either of the images as our test image. Then we can do rotation, like on this image we have like rotated the image. And we can do shearing. Shearing is like square changed into a rhombus operation. So that kind of thing we can do other distortion operations like local warping, which could simulate other effects, other photographic effects. So instead of manually investing the time and money to collect objects and capture thousands of possible uh, variations of the image, we using simple codes, image processing operations, we gather limited input data and basically generate as many variations as we can. And the best thing about it is annotation is also simple because we annotate only the input image, and all the outputs generated using data augmentation have the same label. So it actually saves us a lot of time. And other annotations of other augmentation possible, like changing the brightness artificially or doing giving color shift to represent, say the same person is like this cat is photographed inside of a home at night with a incandescent bulb or a fluorescent tube or out in the sunlight. The color, how it appears, will be different. We can also simulate that using basic image processing techniques.
Now, this image, has it already been segmented, this image of the cat, the primary image?
No, not segmented. This is the input image, and we generate so many variations of it using that. And of course, after that we again have to. There is no segmentation involved.
Okay.
It just happened to have a white background, so we could rotate and zoom along with the background. That's fine.
Got it.
Segmentation is not needed. I mean, in fact, it is not advisable, because we want to keep it in whatever background it has. There is other technique with segmentation. Yes, if you have very less data, then what you do is manually segment the object, and you superimpose this segmented shape with your own collection of random backgrounds and generate more and more images. Like this cat, right? You have just taken one picture of the cat. You could still generate like cat in the park, cat on the beach, cat
Got
in the bed.
Got it.
Using, adding it with
Different
so that
backgrounds.
is also a step. And in fact, in my own professional work, we have done that kind of work as well for certain applications. So yes, background fusion is one of the valid techniques in data augmentation.
Got it.
Okay, so with these, we can mitigate the problems which we began to see with Fashion MNIST, but it just blew off and blew over in CIFAR 10. So if we do data augmentation, and I will in the coding exercises, I will share and I will basically demonstrate how to do this thing, using how to write this in TensorFlow. To automate, TensorFlow provides APIs where we can do the data augmentation like on the data during training as well. So we don't have to process it separately and save it. It can do on the fly. Okay, now we will move from to discuss some of the just one question, Professor Sethi, is it okay if it's like exceeds by about 15 minutes? I think the next content will take about half an hour to explain.
Yeah, that is fine. If you prefer, you can also do it tomorrow, because tomorrow I think semantic segmentation may not take 2 hours.
Okay,
so you decide.
Let's see how far I can go with this.
Okay.
I think half an hour should be fine. So we have around 12 minutes and another 15 minutes. Half an hour I could discuss this, because I'll just discuss the architecture. We will not go very deep into it. We'll only discuss, the innovations that has come in each of the architecture. So we'll not study the whole architecture, because that is that can be done from the original paper itself. It's a long discussion. So the progression of architecture, right? So before 2012, ImageNet challenge. So ImageNet is a long-running competition, consists of many challenges. One of the challenges is image classification challenge category. One of the categories in ImageNet challenge is classification, and the problem is basically if I given an input image, you have to the correct class has to be within the top 5. It's called top 5 accuracy. That means if the image contains a car, then you basically print the top 5 classes that you think are there in the image, and the car should be one of them. So complex images, images which may contain more than one object and all that. And when we apply it, the actual object that we are looking for must appear within the top 5. So top 5 accuracy. So AlexNet was the first convolutional neural net to successfully beat other kind of traditional machine learning algorithms like SVM and other type of algorithms which had winning the competition before. And it was the key point where convolutional neural networks really took off. It got everybody's attention. And so a pretty simple network, AlexNet, is with 8 layers, layers, and it beat. So the previous best result was, I think, around 74%. And AlexNet beat it. Like every year, it used to increase by 1%, 0.5%, 2% with new algorithms proposed. And AlexNet, the jump was like almost like 9.5%. And so that brought this to everybody's attention. And this was key in one thing. It is very similar to the Linnet architecture, just a more layers of the Linnet architecture. Had some interesting trick to train it and all that. But those are not relevant today because at that time the GPUs were of very less capable. So it 5 convolutional layers. So Linnet had 2, it has 5. Linnet had 2 fully connected layers, it has 3, and it used dropout, which is the dropout I have not discussed for this concept because it's the same as which in dense neural networks. Basically, you drop some connections in the fully connected layer, and so it was the key innovation here was it was the first use of ReLU activation. Before that, sigmoid or tanh were more common, and ReLU basically helped properly train a deep network like 8 network. So in 2012, 8 network was a pretty deep network given the computational capacity at the time and the usual consensus at the time. Then immediately next year came another jump of around 8-9%, and just in 1 year. So AlexNet came, and within 1 year the University of Oxford group came up with a VGG16, which basically was a 16-layer network. And the key innovation here was it reduced the number of hyperparameters, like the choice of filters at every stage, how many filters, what size, and all that. It brought down. It says at every stage we'll only use 3x3 filter. We'll use as many stages as possible as required. But so it simplified the building blocks of the network, but expanded on the depth of the network 16 layers, and it reached like 92.7%. Then immediately the next year came the Google Linnet paper, which had 22 layers. It utilized another key innovation, which had come 1 year. So the original network in network innovation had came 1 year earlier. The Google Linnet people used that innovation into a working deep learning architecture. And so that was that. And the network in network block within the Google Linnet is also called Inception module, which is the name is inspired from the movie Inception. I think who was the actor? I think Leonardo DiCaprio was the actor, and there was that famous sentence that we need to go deeper. So 22 layers is pretty deep for 2014, and that was the coincidentally that was the reason for naming the architecture as Inception. And then Microsoft people came up with an important concept of residual blocks, which are skip connections, which we'll discuss just in a few slides. And that had a humongous amount, like 152 layers. And that was the result which actually beat the human performance. So usually the ImageNet, the challenge, right? Given the whatever kind of input images are there, humans are human manual testing. We are only able to get about 95% accuracy. So the ResNet basically beat the human performance for the first time in, I think, the history of machine learning. So with, again, like it came at a cost, like it's 152 layers, which has its own challenges of training and then using. So we'll quickly discuss each of these architectures and what are the key innovations each of the architectures brought, and what we can learn from this to solve our own future problem. So Alex architecture is actually technically 9. After that, there is one softmax layer as well at the end. So when we actually implement it, you end up with 9 trainable layers. Okay, so it used a very complex architecture. It is still the same whole design pattern of the LeNet, but it is like lot of hyperparameters. Like it used input of 227 into 27 into 3 because the complexity of the ImageNet 1000 class data set, right? The shapes, to represent the shapes, you need enough pixels. Like the CFAR was 32 cross 32. I mean, it was all blurry, like all the images are blurry and not very clear. So ImageNet, the resolution is a bit larger. So AlexNet architecture chose 227 into 27 to represent the input. The first layer has 11 cross 11 filters, uses a stride of 4, has 96 filters. Then there is max pool of 3 cross 3, but stride of 2. Like mostly you would expect the stride to be 3, but stride of 2, that means the max pool layer also has overlaps in this architecture. Then the second layer is totally different from the first layer. And this used ReLU. So I'm not mentioning it specifically because this was the first paper which used ReLU for activation all throughout the paper. Other than the last softmax activation in the last layer, every other layer uses ReLU activation. Second layer, again, very different kind of hyperparameters, 5 cross 5, but now same. That means same means padding would be 2 and stride would be 1. And then max pool 3 by 3, again 3 by 3. Then again a set of sequence of 3 convolutional layers without any max pooling. Again, these 2 layers don't have any max pooling to it, but they have the activation function. So convolution, ReLU, convolution, ReLU, convolution, ReLU, then one max pooling. So overall, it basically follows that pattern, but the number of hyperparameters. So it is a very custom-made network, you can say, for that problem. And in fact, like the AlexNet, the network, building of the network and training of the network, it was like very highly targeted towards winning that challenge, winning that competition. So even in the training, they used very heavy data augmentation and a lot of techniques, ensemble techniques. Like they actually trained more than one network with different random initializations and used ensemble of the voting of multiple output of multiple networks to come at a consensus. And basically that is how they beat the all other algorithms with this network. But this is now more or less called the AlexNet simplified architecture because we want to learn about the architecture and not specifically at that today's lecture. We are not interested in how to win the challenge, but learn on this architecture. Okay, then came VGG about a year later. They said, it's too complex to try to find the right hyperparameters. What should be the size of convolution, padding, stride at every stage, and just too complex. So they decided, okay, we will use the simplest things. Convolution 3 by 3 with stride is equal to 1 and same. Same means padding of 1 so that the convolution does not decrease the input image by any size. So that is the most simplest of the convolution operator. They chose that. Max pooling of 2 by 2 with stride is equal to 2. That means no overlap is also the most simplest form of pooling operator. So they just choose these very simple thing and just played around how many times they want to apply this on the network. And what it does is, again, whenever I say conv, the conv includes the activation function. So conv means conv plus activation, and then we have the pooling. So they chose 224 cross 24 color image as an input, and then they have 64 convolutional filters. This is into 2. That means one set of convolution layer with 64, another convolution without pooling, and then a pooling. So yes. We'll come to the concept of transfer learning and how to utilize and build upon the knowledge of previous research in just a bit. It is it used the pooling and then again two consecutive convolutional steps with 128 filters each, followed by pooling, and you can see the whole thing. And ended up with 3 fully convolutional, fully connected layers, 4096, 4096. Again, same. So it does not use different like fully connected layers here. So it standardized everything. The building blocks it standardized, just use as many blocks as it needed. And then have a softmax 1000 layer. One key learning of the convolution layer, where without pooling it, like this effectively does con 5 cross 5. Effectively, like mathematically, it is equivalent of doing con 5 cross 5. Because if you actually derive that, the receptive field of 3 by 3 is 3 by 3, but then 3 by 3 followed by another 3 by 3, it adds one more layer. So it basically effectively becomes 5 by 5. And this set of consecutive convolution 3 times of 3 by 3 is effectively a 7 by 7 convolution. But they kept the building blocks same. They just used the building blocks as many as possible. So this was a good moment in the architecture to actually concentrate on solving the problem rather than forever keep tweaking on the architecture. Okay, and there is a variant VGG19, which basically has couple of steps where they increase this conv 3 to conv like 4 steps. These two becomes 4 and 4. So effectively they become 9 cross 9 filters. And so by doing that, it increases 3 more layers. So this 3 becomes 4, 4, 4 kind of thing. But most of the the community found that VGG16 is as much good as VGG like 19, and just not worth the extra layers and extra computation parameters and extra. So key learning. So if you remember, the LeNet, right, had 61,000 parameters. AlexNet has 60 million parameters. So the number of trainable parameters for the data to learn is about 1,000 times more. And VGG16 is just mind-boggling. Like 16 layers is 138 million. And I think the 19-layer network is around 155 million parameters. So just too much parameters, right? And too much parameters means the model size is very big, takes too much time to compute during forward pass, takes too much time to actually compute. Like you have to compute the gradient for all the 138 million parameters after every like batch for the back propagation, and it's just too time consuming. So the Google people came up with this, like actually the filter, came up with the Google LeNet, but inception module and all that. But the filter in filter concept was first proposed, like network in network concept, or filter concatenation was first proposed in this 2013 paper. So I'll just discuss the concept first and then see how it has been used in the Google people, how they have used to make a very large network, very deep network, but a very computationally efficient network. Because 138 million parameters is just not practical. So to make it even better, if they had to go 200 trillion, 300 million parameters, it would not be feasible to actually have practical uses of it. Okay, so filter in filter concept is like, say in this, we apply a 3 by, say this, in this first layer, we apply 11 cross 11 filter followed by a 5 by 5 filter. Why choose? Why choose whether 5 by 5 is better or 3 by 3 is better? Why not apply same sized filters to the same stage and stack up their outputs. So that is what is the filter concatenation. Filter concatenation is stacking up of outputs. So we apply, say, let's say, this is just an example. This is not, say input layer is 28 plus 28, and the number of number of filters in the previous stage was 192. So the number of channels for input for this stage is 192. And say we apply 32 uh, 5 cross 5 filters, and we apply 128 3 cross 3 filters. They also introduced a unique thing called 1 cross 1 filter. Now it has a use. 1 cross 1 filter is basically a weighted summation of all the pixels in this location along the uh, depth, and along the number of channels. So it's a weighted summation along the number of channels, and so it's effectively a kind of a fully connected layer within this network. That is why is this called sometimes called network in network. So we have multiple types of network, and then there is also a max pooling step, like so. Like this basically max pooling into 32 layers. So it actually, this 192 into 32, that means it's I think 6, right? So it basically combines sets of 6 images and compresses that into picks up the max along those. So it divides it into 6 segments along these channels, and along the each segment is picks the max, like which is the most important feature and all that. So this is not a traditional max pooling in that sense. It's a max pooling in another dimension. So it's kind of this. So this kind of a weird architecture, and we have different number of filters for each, and we use same convolution for all of them. So the output is still 28, 28. And previously we had stacked up filters from each stage. So we now stack up output of all these filters to create a new stack for the next layer. Okay, now a discussion on the computational cost. So this whole structure, right, with certain number of input and certain number of output, and intermediate, we are doing filter concatenation of different types of filters, is called the inception module. So now we'll just see the amount of computation involved. So this 1 cross 1 operation, like 64 filters, from 192, it computes 64 1 cross 1 convolution. This is the total number of operations, which is basically the multiplication addition operations. But basically, operations to be done to apply this filter. And for the 3 by 3, that means this block, the number of operations is this. For the 5 by 5, number of operations is this. I'm not counting the max pooling operation. I mean, it's so it's just a max operation. So it's a kind of a fixed cost. We cannot optimize that. So it came out to be around 303 million operations. So that's pretty high computational cost to do this. Then basically the Google people came up with this innovation called bottleneck layer. Bottleneck layer is, so okay, from this we want to apply, say for this example, this is one part of the network in network. So we want to compute the 5 cross 532, and this has 120 million operations roughly. What they did was introduce one additional 1 cross 1 convolutional operation with reduced number of filters. Now it basically is a bottleneck. Why bottleneck? Because from 192 channel we go down to 16 channels, then again inflate up to 32 channels. So this is like from here it goes down and then increases, and this is why this is called a bottleneck layer. And you think that okay, channel lowering may cause a drop in accuracy, but in practice it has been found that if it is a reasonable drop, it's like you don't go down to like 2-3 layers or 4 layers, like half of the layers, it's fine. But just by bottlenecking into half of the layers and then again inflating and ending up learning all these convolutions, we basically reduce the number of parameters, number of not parameters, number of operations for the forward pass by around 10x. So this effectively computes this with no noticeable drop in accuracy, but this block is 10x faster in the operations. So they introduced 1x1 convolutions everywhere where they could, and so decreased the output for this and effectively brought down the total number of computations for the like inception module to 128 million. And because these are 1x1 filter and 3x3 very small filters, and max pooling has no trainable parameters, overall the inception module has very less trainable parameters. It's a very complex architecture. It is decently computationally expensive. It's optimized still. 128 million operation is not a joke, but the number of parameters to train and all that is much less. So overall, it's a very optimized architecture. And what the Google people did was stack these things up. So initially it starts with a traditional layer, which is like called the base network, which is like three convolutionals. There are some like normalization steps and max pooling steps here. But overall, in this part, there are three conv layers. And then there is a sequence of 9 identical, kind of identical inception network. So this is the same as what we discussed here. This is the inception module. So they have 9 inception modules, and in each we see, okay, there are 2 different layers. So we count all of these which are at the same level as one layer, although they are different filters. So each inception module is like 2 layers. So 9 inception layers is 18 trainable layers, here 3, and there is one more. And the output, there is one more. So total 22 trainable layers. It's pretty good, and it only has 6.8 million parameters. So this actually does better than VGG. This has more depth, can learn more complex things, but the number of parameters, the model size is very small. So portability, right? If you want to have this model in a device which has less memory, so ultimately training is not the key. Training could be very expensive because it is. But after training, you have to deploy the model maybe in a portable device like a mobile or something to do something in an app. And what you like 6.8 million parameters helps you do that. So Google people are very, efficiency conscious, and that basically went in their thought process of this network. And by doing all of these things, they brought down the number of parameters by a very large extent. Now, there is also one more critical innovation that they did was auxiliary gradient injection. So what they learned was, in 22 layers, the gradient, the effect of what error loss, loss function is computed here, the effect of that propagating to the earlier layers is very less. So, but when you train, these layers are closer to the loss functions of max layer, and the gradient has most effect over there, and gradually the earlier layers learn very slowly. They don't change much, and so what they did, innovative thing they did was add these additional, kind of like branches which are only used during training. So they are not useful during the actual inferencing. During training, they computed the softmax loss, and through these like temporary layers, injected the gradient of the loss function into earlier intermediate layers. So like after the fully connected layer and 3 inception layers, they injected this gradient. So they could have directly injected a gradient, but then they would mess up the whole calculation. So these networks, these layers are trained during the training just to add as a buffer between the loss function. So this during the training is kind of a simplified assumption of this whole thing. so that the gradient propagates to this level and then they are rejected. And similarly, after another 3 layers, this is it. So after 3 layers and sixth layer, these auxiliary gradient injection works very well to propagate the effect of the loss function of incorrect classification during the training. And they worked pretty well and they got very good results out of it. But during inferencing, these purple marked blocks are not used. We just go through this main path and output the classifier. And this main path only has 6.8 million parameters, which is the biggest innovation of this paper. So the model size, even with very high quality models, very high performing models, it became very small and became deployable in smaller devices and mobiles, etc. Okay, so the problem that Google people with 22 layers started facing was this vanishing gradient, like backpropagation. The learning speed does not propagate well to the earlier layers. Like first layer in the sense, and is from the behind. So backpropagation does not penetrate well to the earlier layers. Earlier layers learn very slowly. And they solved it using this auxiliary gradient injection. Similar kind of concept, but in a very different thought process, is the ResNet identity block, which was introduced by a paper from, I think, Microsoft China. And what they did was, they learned these parameters to contribute to the classification, but they wanted a much more direct path for the gradient to a part of that. So gradient gets split over this addition operation. So part of the gradient to pass on to earlier layers. So every second layer they added a skip connection and added to the output of the like from the beginning of the first layer to the end of the second layer, they added it. And so that the gradient during backpropagation calculation, the gradient has chance to at least propagate to the earlier layers. And there are other variations. You could skip after 3 layers. Also, you could have introduce a linear layer. So this is without ReLU, so without non-linear. So add a linear function to learn learnable parameters of linear functions within the skip connection. So there are other variants. And what they ended up with is something like this. Like in this bottom layer, it's a 34 layer ResNet. So ResNet models are different, like 34 layer ResNet, which is actually called ResNet 50 because ResNet blocks are 34 layers. There are other fully connected layers and initial convolution layer and all that. So total layers are 50. Total trainable, learnable layers are 50, but the ResNet layers are 34 only. So that means 17 blocks of ResNet pairs are there. So every second there is a skip connection. Sometimes the skip connection is omitted. And this actually, even with a very deep network like 50 overall layers, it has successfully is able to affect the gradients even in the earlier layers through these linear skip connections. And that also helped here because the size only is like the screen, the resolution, I only showed the ResNet 50. Very similar architecture, just more and more blocks is ResNet 101, and then there is ResNet 152, which actually beat the human performance on ImageNet challenge. So ResNet 152 is similar architecture, just expanded a lot of repetition of the same blocks. So these are the key things to learn here. Like ReLU came, then simplification of architecture came. So hyperparameter search on the architecture became simpler. So even you can see that in Inception, it's basically same building blocks repeated multiple times. So they don't bother about changing the parameters from stage to stage. It's practically the same repeated architecture. Google guys introduced basically made use of network in network architecture, introduced the bottleneck layer for computational efficiency, introduced the auxiliary gradient injection, to solve the slow training issues of very deep layers. So very lot of innovations there. ResNet guys solved this innovation to a very deep network. So very deep networks have only been possible with ResNet. And there are now combinations of Inception with ResNet, which are very, very deep. Like Inception version 4 model is there, which is a very deep layer with combinations of Inception concept along with ResNet skip networks. So ResNet is a very important. The skip connection made very deep layers possible. Very deep layers can really learn very complex things, but the problem always was training. It did not converge fast enough, and with this ResNet, it's a breakthrough. Okay, so now if there is a little bit time, I can just talk about it. It's just 2 more slides. So as you can see that, a lot of big networks have started coming in, and they have been trained, like the ImageNet data set, right? The overall ImageNet data set is around like 14 million, I think, images, and it's just huge. And as you can see, right, millions of parameters and 152 layers. It's very expensive to train these networks, and so it actually makes a very practical sense to not try to build and train networks from scratch anymore, because like the source code of the models most often these days is published by the authors themselves, and it put into the public, like GitHub and all that. So if you find a paper with a very nice architecture, if you search for the author's name in GitHub and stuff, you'll probably find already an implementation released by the authors, because they want adaptation of their algorithm in the community, so they generally tend to release it. Once they have published the paper, they have been attributed with the intellectual property. They release the architecture implementation, and most often with the common framework of your choice, like Cafe or PyTorch or TensorFlow, very commonly available. Open source model, and also the pre-trained model weights, right? Because they have invested, thousands of hours annotating the data, and then weeks and months to train the model on very expensive GPUs and stuff. Uh, they release the model weights, and it makes sense for us to use it, because we don't have to put in that amount of server cost in training the models. So it saves us time, it saves us money, and saves us hardware investment, and also it saves us the hassle of hyperparameter tuning. There is a model which works very well, why don't use it? And why can we use it? Now the question comes, we can use this, but what if our problem is different from what they're trying to do? It turns out that transfer learning works very well in computer vision. Why? Because the whole premise is that the early and the mid layers of the CNN, right, they perform generic image processing. They are ultimately kind of learning generic image processing and feature extraction. Like they are learning to find the building blocks, right? Edges, corners, blobs. And whether I want to build a face or no face, like human classifier, or I want to build a cat versus dog classifier, the basic elements, the geometric elements that build up shapes, right, they remain the same. So whatever has been trained on one problem very easily in computer vision domain applies to uh, any other application area. So what we can do is freeze this kind of, we can call that like freeze these layers, which is that means that whatever the weights have come up from there, we'll just take them. And we only train the rest of the network, and which mostly is the classifier part of the network. So the feature detector part of the network, the convolution layer, right? This is most computationally expensive to train. We utilize that using we just pick the weights, pick the models from open source, either pick the classifier stage directly and just retrain the models, or have our own classifier stage, whatever the use case it is, because original network may be doing 1,000 class classification, your case might be a 10 class classification, so you have to modify the classifier stage. Anyway, what we do is freeze the layers and train a small alternative. Either we train the rest of the network or train an alternative network uh, according to our own needs. and usually the frozen is the fully connected layer. Sometimes we also retrain like the last few convolutional layers, but depends on how much data we have, uh, and how similar or dissimilar our application area is from. Like cat versus dog problem may apply very well to human, like face or no face problem, but sometimes if you're trying to do say medical image processing, it may not generalize that well. So in that case, maybe we have to retrain whole of the CNN, or maybe one or two of the last layers of the convolutional layers as well, to have better results, because the domain of the problem and how it looks, right, it bit different from. So like cat, humans, there are natural images generated using light photography, but if you do a CT scan, the process of generating the image is very different. So sometimes it depends how, similarities, and plus how much new data. Sometimes even if the problem is very different, we don't have access to much data, so we must make do with whatever we have, and utilize this. So these are the basically the key training techniques of utilizing the latest architecture innovations in very deep, expensive networks, and how we can utilize it for our own applications. And in the tutorial, I'll also explain how using TensorFlow, very easy to do transfer learning. Like we can just, load one open source model, initialize it with given weights released by author or some other third party, and then just unfreeze some of the layers, last layers, train them according to adapt the problem to our own problem, and basically have a very quickly have a solution at very low compute cost. So overall, this is the content. It has been a bit heavy lecture, kind of, because we compacted like 2 lectures into one. Uh, if there are questions, I would be.
I just have one question.
Yes.
Whenever we use TensorFlow and for object detection, and it is able to detect multiple objects like book or a pen or whatever, is that
Right.
transfer learning in play or something else?
Yeah. So adapting transfer learning is what, whatever knowledge we have learned from one application area, we try
Okay.
to apply that knowledge to another application area with minimal effort.
Got
Because
it.
doing the effort from scratch is just impractical nowadays. In the
Got it.
LeNet
Got it.
era, or even in the AlexNet era, it was possible. But the amount of, like, even Google LeNet, I mean, if you try to train from scratch,
Okay.
if you train it on a cloud server, it will cost you thousands of dollars of training time.
Got it. Got it. Got it.
And also it will require a lot of data. Like they have trained it on like 14 million images, and so in your
Got it.
application domain, you will need to have that many amount of data. Otherwise, you will end up with overfitting.
Okay. Okay. Okay.
So it's not just the cost, it sometimes is not feasible. Like if I say, CT scan, probably an average researcher may not have access to 14 million CT scans. I mean,
Yes. Yes.
it's very
Yes.
difficult to get. I mean, camera natural images, you still get it from the internet, but
Yes. Yes.
like medical images, so many, it's not easy. So
Yeah.
it's like that. So you see, you basically do kind of judgment. Like you first try with only unfreezing the classifier layer and see
Okay.
how well it does. And if it does not do well, then you try to push into more and more layers. And so, but still, like, you limit your like effort, time, and cost into this.
Yeah, and this all depends on how similar the problem that we are trying to
Yes.
solve. Let's say, okay, let's say we are trying to classify car models or whatever, then it makes sense rather than going for a completely different set of images. Then,
Right.
okay,
Like car is natural image, the same illumination effects, car and
okay,
person, although they are different shapes,
okay, okay,
but because they are photographed in a similar fashion,
okay, okay,
basic geometric parts may be similar, same
okay,
curves
okay.
and straight lines and stuff. The problem kind of applies. And it is
Okay.
not just that. Actually, the funny thing is, you like VGG, right? VGG
Mhm.
has been trained for classification,
Yeah, yeah.
but the like FC7, it's a very common application
Mhm.
in just show you. So FC7 is basically this layer. So the output of this layer actually has been very well adapted. The output of this fully connected layer has very well been adapted. Sorry, it's not this. Sorry. This one. Output of this layer has been very well adapted to image segmentation problem. Like many segmentation architectures actually use the VGG16 backbone. So the VGG16 was not only trained on different data, but it was trained for totally different application. It was trained for classification. Classification is a basically like binary problem, and segmentation is a pixel versus pixel problem. But still,
Yes.
kind of it applies. So the VGG
Okay.
network backbone is a very common like backbone in some segmentation problems as well.
Okay.
So you would so this is the beauty of like computer vision domain, and because the convolution thing is only learning features and how to describe something, it is not actually learning an object, but it is learning the methodology how to describe an object. That understanding works well in different application areas and even totally different use cases. Yeah.
Okay. 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 Thank you. Thank you.
If there are no more
Ashish,
questions,
Ashish, did you have a question? Go ahead.
I had a question like recently, like I don't know whether you are aware about it, but around 21st of May, there is a thing called big transfer, right? Google actually came up with their new, like they open source their models. The paper came out much earlier, but I think they
Yeah.
have given the weights and everything. So if you are aware, probably tomorrow you can, like I wanted to know when using that would be useful, because like the transfer
If the
learning
model is
converges
available, the weights are available, you can use it now.
I mean, the
Right
point
out.
is, yeah, the point is it converges faster. Like it's like, like the new version of transfer learning. But still, I wanted to at least know that, in what applications still using the previous backbones would be useful as compared to that, because
It depends on your application, right? See, in your application, whatever you have the data and whatever use case and whatever the quality requirements of the network, if you are able to achieve it using existing, fine. You say it's like, if something isn't broken, why fix it? So it's like that. So if you are hitting a bottleneck and you think whatever new improvements have been introduced in the new paper that will help in the specific problem you are facing, try it out. And especially if it is model and weights have been made open source, it's not much of an effort to actually try it out. Probably 1 or 2 days you can understand it and fix it up for yourself.
sure.
Could be
Thank you.
possible. So it's like that. It's two questions. Like if it works well using previous architectures and you have already solved the problem, let it be. Or unless you are in academic research where you want to try it out and try to further improve on it, then try it out today.
I mean, the idea is that this is also like, for example, we all like you covered many architectures, right? And there was
Right.
an interesting thing that came out that VGG16 is the backbone of most image segmentation.
Right.
So this is some interesting property
Not
that
most, I mean, it has been
VGG16.
used extensively. Of course, like Inception also has been used in other different problems. And ResNet backbone is actually becoming common now. Like this
Yeah.
ResNet 34 backbone, right? Without the fully connected layers and flattening and stuff. The basic ResNet 34 or ResNet 101 is being used for other applications as well. So VGG came earlier, so VGG has been used earlier. Many are using ResNet as well, Inception as well. So depends.
So is there any consolidated place where all these properties are mentioned or something like? I mean, I would want to go through this. This is quite
Not I
interesting.
mean, there may be blogs. There may be blogs where they have specifically discussed like You may find it, if I may find it, or somebody in the group may find it and post it.
I mean, the stuff like the pragmatic stuff that you talked about, for example, VGG16 is used extensively at the
Yeah.
backbone.
So this is basically the experiences of people, right, who have used it and all that. So
Sure.
probably could there be in some, usually maybe in a blog or something where they have done comparison and maybe some kind of market study, how many people are using this, that.
I mean, I think I can also start a post on Campusfire and you can comment with whatsoever, like you talk
Sure.
spontaneously
And
about it.
before
And
you do that, and along with that, you can also search whatever you
yeah,
are
sure,
looking for,
sure,
right?
sure, sure.
You can just search,
Sure.
comparison of VGG usage versus, say, Inception versus ResNet, something like that. You'll probably end up with either some kind of white paper or some kind of blog post which talks about these things.
Yeah, sure. Thank you.
I have read it. I don't have it bookmarked or like right now open with me, but yeah, that kind of are there. Resources are there. So people have talked about it. They have compared it. They have even checked, like, find out what is the penetration of each of the types in different applications. Like how many products are using this, how many products are using that. That kind of market study is also there. Yeah. If no more questions.
Yeah, just one last question. How do they do, or will you cover it later in the course of how they do segmentation in real time? Because images are fine, but when you have a live stream to do segmentation, and that is entirely
I'm
different.
not sure. Is it being covered on the syllabus? Maybe. I don't know.
Okay.
Segmentation, I am not taking, so I'm not much idea on what is the actual content within the syllabus.
Okay. Thank you.
Okay. So whatever the concept, this was mostly theoretical and conceptual lecture. Especially, but in the tutorial, we will basically see how we arrive at these things, and also learn about how to implement data augmentation using TensorFlow, and also see how to code complex. Like in the previous tutorial on Saturday, we learned how to code very simple architectures. So complex architecture like this, or maybe even this, how to code it up in TensorFlow. We'll probably see how to encode one of these blocks and then repeat the blocks, stuff like that. So we'll see, and we'll also see how to utilize the TensorFlow API functionality to achieve our transfer learning goals in the tutorial. Right.
Okay. Thank you.
Okay.
Thank you.
Yeah. Thank you, everyone. I mean, it's yeah. Thank you for the patience. It went on quite a long time.
All right. Thanks, Sumandeep.
Yeah. Thanks, Professor. Yeah.
Okay.
Okay.
Okay. Good night, everyone.
Yeah.